All right, class, today, on Friday, you were supposed to watch Flipping Physics that had to do with uniformly accelerated motion. And he taught you the 5, 4, 3, 2, 1 rule, which is where I got that 5, 4, 3, 2, 1 rule. Okay. And I use it for teaching this material. It's awesome. And I like the repetition of it. I like the rhyme. It's catchy. It helps you remember. And it gives us an approach to solve these kinds of problems. So I'm going to go over kind of where all this came from and this is exactly right out of the book. This is 3.2, but we're going to use this 5, 4, 3, 2, 1 approach to solve these kinds of problems. So what is UAM? That's uniformly accelerated motion. That means acceleration is constant. And so if you recall, when an object has constant acceleration, the velocity over time curve will be linear because the slope is equal to acceleration. And if the acceleration is constant, which is what UAM stands for, uniformly accelerated motion, then this is constant across that line. So that is exactly what that graph looks like. And similar to what we did in the past, we can use the equation of the line, which is y equals mx plus b, and develop another very useful equation related to the intercept and what the definition of slope is in this case, which is acceleration, and what the variable, the x-axis is, which is time. So we have our velocity time equation, okay? And I'm going to go through this quickly because I'm going to teach you, I think, an approach that I have found that CP students and my AP students, generally this works very well. So let me just get to, what we start doing is we start having all these equations, and there's quite a few of them, but they all came from the mathematical relationships that we have developed using these position versus time curve, velocity versus time curve. So the first one you learned, which I'll call equation 1, is from a position versus time curve. That was that equation of motion that we used on our chapter 2 test. The final position is equal to initial position plus velocity average times time, and the velocity was the slope of that line. And now we have what is the definition of average velocity? Well, if you take an average velocity, so now because acceleration is impacting our velocity and its velocity is changing, we don't have a constant velocity anymore. We have to actually, we can take an average velocity, the final plus initial divided by 2. That's what the definition of average is. So, and then we can plug those, we can derive all those equations. So we derive these equations. This is the average velocity right here. This is average velocity. Okay, and so by using and combining this equation, I have created my next equation, okay, which is x final equals x initial plus v initial time plus 1/2 at squared. And then we have another equation, which I'll call equation number 4, okay? And that's just taking some additional graphs and combining some more. And I'm not going to derive that for you because I don't know that it's of value to you. So my summary is, yikes, you're starting to have a whole bunch of equations that you have to use when we have constant acceleration. So we're going to have, this is my approach. UAM problems, we have 5 variables. And if you were in class, I'd make you say this over and over again. How many variables are there, guys? 5 variables. And then I make you list them. We have 5 variables. We have 4 equations, which you have on your equation sheet. If I know 3 of those variables, I can solve for the other 2. And that makes for one happy physics student, happy teacher, happy parent, because you have an A in the class. 5 variables. What are the variables? Well, here they are. You've got to be able to you have to be able to list off the 5 variables. Well, a change in position, the initial velocity, because the velocity is going to be changing now because I have acceleration. The final velocity, okay, the acceleration and the elapsed time. So I could put delta t there if I wanted to, but I'm going to assume initial time is 0. So the elapsed time. There's my 5 variables, okay? And here are my 4 equations. And notice I have the 5 variables listed there, all right? There's my 4 equations. Delta x is equal to the average velocity, which is 1/2 times the 2 velocities added together. I just took the average of 2 numbers times time. V final is equal to V initial plus AT squared. Delta x is equal to V initial times time plus 1/2 A times t squared. What does that little subscript x means? That's in the x direction. Okay, I can apply it in the y direction if I want to, and then I call it delta y. V final squared is equal to V initial squared plus 2 times the acceleration times the displacement. So there's my 4 equations that I'm going to have. And we're going to actually go and solve a problem or two using that. We're going to actually we're going to stop, and we're going to be on section 3.2 for a couple days, and we're going to work problems, and we're going to apply the 5, 4, 3, 2, 1 rule. Okay, so I'm going to give you whiplash. Okay, so here's example 3.6. Approached using my 5, 4, 3, 2, 1 rule. You throw a baseball upward with an initial velocity of 8.2 meters per second. Gravity gives the ball downward acceleration of minus 9.8. What is the velocity of the ball after 1.5 seconds? Okay, where's my table? What is delta x? Well, you know what? We're in the y direction. So let's use delta y. Okay, so I have a pitcher. I have a ball. I threw it straight up. And I'm going to list all my variables. Well, what is my first variable? Delta y. Did they give me delta y? Did they give me the height, the change in position in the y direction? No, don't worry about it. That's okay. I don't know. All right, V initial. Did they give me that one? No. Oh, yes, they did. They did right here. That is my velocity initial. So 8.2 meters per second. Gravity. Did they? Okay, hold on. I'm gonna list all of them. I don't know the final. They didn't give it to me. They gave me the acceleration. Okay, so I know that acceleration is negative 9.8 meters per second squared. Okay, and I notice that this is the positive direction upwards. Okay, they gave me time, 1.5 seconds. Now, what do they want to know? What's the velocity of the ball after 1.5 seconds? What velocity is that? That's the final velocity at 1.5 seconds. Okay, so this is the question mark. This is the one I'm looking for. Okay, now let's list all of the equations. Delta y is equal to 1/2 times the initial velocity times the final velocity times time. That's just the average velocity times time. This is the definition of average of two numbers, right? Add them together, divide by 2. The next one is V final plus V initial. I'm sorry, that is not it. V final is equal to V initial plus the acceleration times time. Okay. The next one is the change in y is equal to V initial times time plus 1/2 a times t squared. Okay. The next one is V final squared equals V initial squared plus 2a delta y. So there's my 4 equations. Now my favorite equation is this one. I say that because it's easy and it's straightforward. And I'm going to look at that equation first generally. All right. Can I solve the question? Do I have enough information to solve what they're asking for using that equation? Well, let's see. What am I looking for? I'm looking for final velocity. Okay, well, good. It's actually got the variable final velocity in the equation. That's kind of a key, right? All right. Do I know the initial velocity? Yep, they told it to me. Do I know the acceleration? Yep, they told it to me. Do I know time? Yes. So I actually can use that equation. V final is equal to V initial plus A times T is equal to 8.2 meters per second plus a negative 9.8 meters per second squared times time, which is 1.5 seconds. So V final is equal to, okay, so after plugging that into the equation, I find that the final velocity is negative 6.5 meters per second. Well, that's weird. A negative 6.5 meters per second. What does that mean? Well, don't stress. The ball went all the way up and then started to come back down. And it was a long enough time that my velocity is now pointing back down towards the direction it came from. Okay, we're going to learn more about that very soon. All right, so the final velocity was negative 6.5 meters per second. So it was coming back at me at 6.5 meters per second after 1.5 seconds. So let's do another problem. A boat moves slowly inside the marina with the constant speed of 1.5 meters per second. So here's my boat, and it's moving at 1.5 meters per second. As soon as it leaves the marina, it throttles up and moves with a constant acceleration. So now I have an acceleration of 2.4 meters per second squared. What is the initial velocity of the boat after accelerating for 5 seconds? Okay. And how far did it travel during that time? So let's make a list of all of my variables. I'm going to call this in the x direction. So delta x, I don't know it. They asked for it, so we're going to have to find it. V initial, did they tell me it? Yep, they told me that it started off at 1.5 meters per second. So we need to identify that as my initial velocity. Final velocity, did they tell me that? No, but they asked for it. That's actually this right here. That's the final velocity. Acceleration, did they tell me it? Yep, 2.4 meters per second squared. Time, did they give it to me? Well, they're going to have to, because I have to have 3 things in order to solve this. So they gave me 5 seconds. So here's the 3 things they gave me: 2.4, 1.5 meters per second on the initial. I've got 3 things. If I have 3 things, I 100% can solve this problem without a doubt. I can find those other 2 variables. And now I need to think to myself, what are all my equations? Delta x is equal to the average velocity. So there's the definition of average velocity times time. Then my favorite super easy equation, which is V final equals V initial plus A times T. And then, so let's start off with this, see if we can answer the first question. What is the velocity of the boat after accelerating 5 seconds? So let's look at this. They want, what does that mean? That's the final velocity they're asking for. I know the initial, they gave it to me. I know acceleration and I know time. So I can use that equation to solve this problem. And that's actually, in my opinion, students struggle the most at trying to figure out what equation to use. V final equals V initial plus acceleration times time. What is my initial velocity? It's 1.5 meters per second plus the acceleration, which is to the right at 2 meters per second squared. So I'm speeding up, by the way. And I have a time of 5 seconds. So 1.5 times, or I'm sorry, add 2.4 times 5. So I get a final velocity of 13.5 meters per second. Okay, that was A. B, how far did the boat travel in that time? Well, if I know the final velocity, now I can use the fact that the change in displacement, the distance it traveled in the x direction during that time frame, is equal to its average velocity times time. So let's use that equation. Delta x is equal to V final plus V initial, that value divided by 2, that's the definition of average, times time. Now let's plug in some numbers. So that is equal to the final velocity, 13.5 meters per second, plus the initial velocity, 1.5 meters per second. All of that divided by 2 times the time, which is in 5 seconds. Units of seconds cancel, and I get an answer in meters. So 13.5 plus 1.5 divided by 2 times 5, I get an answer of 37.5 meters. So there is the answer for B. So what I want you guys to do is try using the 5, 4, 3, 2, 1 approach. 5 variables, 4 different equations. Those equations are on your equation sheet, which are located right here. There they are. And I've basically plugged this into here. Okay, that is the average velocity, definition of average velocity. Okay, so there's your equation sheet. And my request is that you work 23 and 24 and try to apply that and practice trying to figure out what equation, list your 5 variables, fill in what you have, try to figure out what equation you can use to find the thing that they're asking for. Okay, have a good day. Come see me if you need help.